Okay, so this time we're going to finish our investigation of stationary points of functions by investigating the stationary points of a function of n variables, x1, x2, all the way up to xn. So that's n variables. Now, we can't really start the same way we started before. We can't start by drawing the function because we can't really draw a function of more than two variables. So that's why we don't treat the three-dimensional case. We just say, well, we might as well treat all of the cases at once for any arbitrary number n higher than 2, or indeed equal to 2, or indeed equal to 1. This should generalize and cover all the cases before, but it was worth studying them explicitly because they prepared us for this case now. So instead of drawing the diagram, we just skip to the point. We skip to what we're trying to do. Well, we start at some point with coordinates x1, x2, all the way up to xn, and we make all these displacements to a nearby point with coordinates x1 plus h1, x2 plus h2, all the way down to xn plus hn. And as a consequence, we expect f of x1, x2, and xn to become f of x1, x2, all the way up to xn plus delta f. And this delta f is what we're trying to investigate because delta f is going to be our change. So delta f is going to be the end minus the beginning. So it's going to be where we ended up, f of x1, x2, all the way up to xn, minus our start point, which is f of x1. Oops, of course, please excuse me. That's f of x1 plus h1, f of x2 plus h2, all the way up to xn plus hn, and of course minus f of x1, x2, all the way up to xn. And if our function is stationary, we hope that for small displacements h1, h2, dot, dot, dot to hn, we want this to vanish. We expect this to vanish to first order in the displacements h1, h2, all the way up to hn. And this is going to be what we mean by a stationary point of a function of n variables. So this is the same as saying that the point x1, x2, dot, 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 xn is a stationary point of our n-dimensional function f. And this is our most general definition so far, so definitely worth boxing this one up. So now we play the same game we played twice before. We investigate this delta f by first investigating this f of x1 plus h1, x2 plus h2, dot, 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 xn plus hn. And again, we just use Taylor's theorem in n dimensions this time. So for the one-dimensional case, we use Taylor's theorem in one dimension. For the two-dimensional case, we use Taylor's theorem in two dimensions. And for the general n-dimensional case, we're going to use Taylor's theorem in n dimensions. So it's going to be f of x1, x2, dot, 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 all the way up to xn. And we're going to add in h1 times the partial derivative of f with respect to x plus h2 times the partial derivative of f, so this is x1 with respect to x2, and the partial derivative of, h3 times the partial derivative of f with respect to x3 plus dot, 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 all the way up to h4, hn times the partial derivative of f with respect to xn. And we know that there are going to be second order terms and third order terms and fourth order terms and so on, but we just like to package them up the same way we did before in this big O of mod h1 squared plus h2 squared plus dot 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 plus hn squared. So this is the norm of the displacement. So this is just big O of the actual displacement of second order displacement. So any term of order that goes like h1 squared, h2 squared, all the way up to hn squared, or any order higher than that, we treat those as negligible. Now, again, we are now going to compute delta f by moving this f of x1, x2 all the way up to xn to the other side. So we're going to have f of x1 plus h1, x2 plus h2 dot dot all the way up to xn plus hn, and we're going to subtract f of x1, x2 dot 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 all the way up to xn, and well, we're going to have whatever's left on the right hand side, which is h1 df dx1 plus h2 df dx2 plus dot 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 all the way up to df dxn. And of course we still have our higher order terms, big O of mod h1 squared plus h2 squared plus dot 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 all the way up to hn squared. And again, these displacements h, all of these displacements here, so this is hn, these displacements here are all very small, but critically not zero. Right, so as small as we like, but not zero. Therefore, because these aren't zero, and because we treat this term as negligible, the only way for delta f to vanish is if df dx1 is equal to df dx2 is equal to dot dot dot, oh sorry, to all the ones in between is equal to df dxn. If all of those vanish, we say the point x1 x2 dot 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 xn is a stationary, oops, let's just make some space here, is a stationary point, oops, let's make a new one and scroll up a bit, is a stationary point of the function f, okay? And again, we can play the same game before by packaging these all into a gradient and writing that, of course, the gradient of f vanishes. But this is the n-dimensional gradient involving n unit vectors. And now we can just box this off as well to complete our investigation of stationary points of functions. And next time, in the next part of our lecture, we're going to generalize this to functionals, which will culminate in the famous Euler-Lagrange equation.